Good afternoon to one and all present here. It is not the strongest of the species that survives, not the most intelligent that survives. It is the one most adaptable to change by Charles Darwin. I never see what has been done. I only see what remains to be done by Marie Curie. By quoting this, with the blessings and support of our management, I, Dr. Shubha, Professor of Chemistry, welcome you all for this webinar. We have an eminent scientist, Dr. M.V. Reddy, with us today. Dr. M.V. Reddy obtained his PhD degree in the area of material science and engineering with highest distinction from the University of Bordeaux, France. From July 2003 to May 2019, Sir worked at the Department of Material Science and Engineering, Chemistry and Physics, National University of Singapore, Singapore. From June 2019 to August 2021, Sir worked at the Center of Excellence in Transportation, Electrification and Energy Storage, Hydro-Quebec, Canada. Currently, Sir is working as a senior professional researcher at New Graphite World, Montreal, Canada. Over the past 20 years, Sir has conducted leading research in the field of materials and energy storage. In the field of supercapacitors, solid electrolytes, solar cells, electrocatalysis, photocatalysis, and evaluation of functional properties of materials and development techniques and materials for renewable technologies. Dr. Reddy has published around 200 papers in various international journals. Sir has obtained an H index of 66 with over 17,000 citations. Sir, it is quite difficult to see this 17,000 citations for common and very small researchers like me, sir. These have recently placed him within the top 2% highly cited researchers in the field of energy. Dr. Reddy is serving as an editorial advisory board member in Materials Research Bulletin and Journal of Energy Storage. Those are published by elsewhere. Sir has conducted several workshops and delivered plenary talks, keynote addresses, invited talks, contributory talks at various national and international conferences. For his credentials, Outstanding Science Mentorship Award from 2010 to 2018 from Ministry of Education, Singapore. Sir has received Inspiring Research Mentor Award from 2011 to 2019 from NUSHS. In 2021, Battery Materials Electrochemistry Award from the Electrochemical Society of India, Indian Institute of Science, Bangalore. Sir has invited life member in the International Center for Diffraction Data, USA. He is an elected committee member in Institute of Physics, Singapore from 2015 to March 2018. Materials Research Society, Singapore. He has elected in 2 times, 2016 to 2020. Sir has served as an honorary auditor, IPSS and MRS, Singapore. Global Materials Network till now. Sir has served as a theme chair and session chair for various international conferences. Sir has trained more than 250 students for BTech, MSc and PhD programs, international exchange programs, and Sir has guided 7 students for their PhD degree in the field of electrochemistry, applied physics, material science and engineering. With this brief introduction, on behalf of Don Bosco Institute of Technology, Principal, Department of Chemistry, I welcome you, sir. Sir, I welcome you, sir. Over to you.
Very much, madam. Okay, now it is okay. So
yes,
again,
sir.
Can you help me to activate my?
Yes, sir. Yes, sir. I am making you as a presenter.
Yeah. Now it is working. Now it will work. So once again, hopefully it is all right.
Yes, sir.
So again, good evening, everybody. For me, it's almost morning 5 o'clock, 5:55. So once again, thank you very much for your kind introduction, Madam Shubha, and also Dr. Manjunath for his kind invitation. and also the principal and all management of the Don Bosco Institute of Technology. In fact, I'm first time I'm presenting to you with your school virtually. Okay. Once again, thank you and all the especially for the attendees. So since as suggested Banjanath, I think many people from students and also some PhD students, I try to talk make sure it's a little bit more simpler so that like since audience are mixed, so that I'll try to include some few slides. It will be useful for both chemistry, physics, and engineering, including electrical or sometimes mechanical, etc. Or some slides may be useful for management also. At the end, it is very important. Okay. So, so again, I think today, although this title is since the chemistry department, I made it as a electrochemistry. So again, it looks like it is a multidisciplinary research. So I'm going to maybe since I think for you the evening, maybe I'll try to finish my presentation within maybe 45 to I think 55 to nearly 55 minutes. So just I'll try to put my timer on so that okay. So presently, I based in Quebec, both French and English-speaking colony. In addition to the other climate, especially here, you can see that we can say especially low temperature. Maybe now January, the extreme some few days it may go to extreme cold climate also. So these outline of presentations I am going to introduce, followed by importance of these fundamentals, and then few related to the EVs and material recovery, etc. I think all people are. So what I'm mentioning that since you have facilities and then everybody can do the battery research, so it's not a many. So only thing we need a little bit infrastructure. So these are the small examples. So some of the students have been trained with the high school and junior college students at the National University of Singapore. So interestingly, what I'm mentioning that some publications also be published based on the junior college and high school project students. Some students like us, they're able to present in the various national conferences, especially science and engineering fair. And a few students are able to participate in the overseas international conference held in USA and few places in Poland, Europe, and Japan, etc. So these are a small group from NUS as well as nearly 6 to 7 students have been trained in our group from India. Mainly, a lot of exchange PhD students have been trained. Most of students have finished the PhD in our laboratory and then submitted to the respective universities, and also a few other people from other part of the world. So these are the small collaboration within Singapore and India, and also a few other part of the world. So regarding the research is concerned, mainly I'm focused on the some novel materials for lithium and sodium, etc. And also we know that once we know the technology may be same, we can do either you can play with the lithium, sodium, but only you need to change the what they call counter and reference electrode or electrolyte, etc. I'm going to discuss about the what are the difference between the lithium, sodium, and then or people will call it magnesium, aluminum, etc. Anyway, you can do electrochemistry since you are electrochemist. You can do with the same facilities. You can do interesting electrochemistry. Only thing is that depending on applications, use their materials they're looking in terms of the what they call energy density and power density, etc. So anyway, other areas since what I'm mentioning that sometimes we cannot do all I5 research. So still with use of electronical techniques, I think people have interest. So with aqueous electrolyte, you can do some supercapacitors. So and also still you can play with electrochemistry. And again, it is I told you it is multidisciplinary. Sometimes the electrolyte itself is including the solid or polymer or inorganic electrolytes also can play. Another area is the lithium air, just one set of putting coin cell. You can try to expose the material in the air, they color the air type of the cells. Again, each technology been what they call the limitations and then advantage, disadvantage is also there. So, and also, anyway, sometimes so if you have some nanomaterials, you can play with different type of applications. Again, sometimes you're a physicist, since you do have this sputtering unit, you can do what they call a thin film micro batteries. Also, you can do again. You need a lot of time and effort, and depending on what type of available facilities. And same if you have thin film technology, then instead of stainless steel substrate, you can do with some other type of substrate like electrochromics also you can do just to see the color change, what they call a smart window, etc. So again, I think sometimes it is very important to understand the in situ spectroscopy as structural studies is very important, either to battery material or any type of the supercapacitor or any type of material. I think in situ techniques are very useful to understand the mechanisms of the materials. So now, I think it is very important. Always people are talking about the what type of the hot areas. I think now in energy, environment, and uh, healthcare and water technology. I think that are very very hot area, and also it is useful for the society. So that's why the people are irrespective depending on facilities. People are concentrating on this main area, and in addition to this one, energy itself, it is a multidisciplinary, sometimes all category of engineering also involving. So that's why I don't tell that it is very one particular to the one area. And again, as a researcher point of view, sometimes it's our responsibility to think to maintain the sustainable environment, and especially to reduce the air pollutions or the and healthy lifestyle. And also people are talking about the smart city development. For that case, we need a smart transportation or waste management, etc., etc. All this one, always people are call about smart. So again, the classification of materials, we broadly classify it based on the utilities, call it construction materials, phase change materials. Sometimes if people are working with solid state electronics, I think silicon, germanium, and these are semiconducting materials are very important. And explosive, energetic materials, engineering, for example, mechanical engineers. So people are looking for some lightweight alloys, super alloys, understanding that. So this is also very interesting and also useful for the applications. So again, based on physical properties, we broadly classify metal, semiconductor, insulators, magnetic material. Again, it is more on physics. Sometimes although you can do, so it is, and optical materials. For example, again, you can do, for example, a different application like photonics applications, etc. And dielectric, radioactive. I think today we are going to focusing something like energy storage material. Maybe we can use it for the same material used for electric vehicles or a smart grid or your mobile phones, etc. Again, although technology with mobile phones have been mostly, I think, since it's due to energy requirement, the technology is a little bit simpler. If you go for electric vehicles or smart grid, again the cost, and then especially in terms of safeties and some of the other things has to be solved. So now I think always people are talking about the green environmental problems. I think we need a green renewable clean energy technology. Among them, again, the this it will vary depending on what type of available sources. For example, India we have like huge, like some nice sun reasonably compared to here, and especially here the good electricity hydro. That's why hydroelectricity is the main source. That's why, and other forms of biofuel and hydrogen storage, etc., and that wind, mechanical, nuclear, geothermal, etc. Again, I think the batteries are very important one. So why mentioning that mainly 62% or 60% of the pollution in the major cities is coming, irrespective of any place, the pollution is coming from the uh, four-wheel cars. That's why people are thinking about the why don't we replace that gasoline car by battery operated car again. So due to cost of the petrol, there are all things to take into consideration. I think that's why people are considering with the long term how this technology may be useful, and then especially solve in terms of the environmental, especially to reduce the pollution. And also people are, especially in addition to this one, cost is also major things to be, especially all common people want to use. So cost is a major criteria for the, especially this EV technology. Now another important point, again I'm mentioning the energy storage renewable. I think these are all the common word is interdisciplinary of science. I think again we need the importance of chemistry. So chemistry itself, we can, it is not like it we need organic chemistry background also, sometimes physical chemistry, electrochemistry, and inorganic chemistry, sometimes polymer chemistry. So all the areas is very important. That's why you have to focus, and also sometimes again the physics in, if you want to take material characterization, again we have to understand the like for example structure, all this one, again the physics either you can do, or sometimes the electronics, etc., is very important. In terms of engineering, again we need materials production, especially chemical and mechanical, civil, electronic, and automobile. At the end, I think we need a management also is very important. Whatever the things you do, if you go to industry, I think we need a good management. That's why it is always everything is a interdisciplinary. So now it is very important. I think if you take any EV vehicle, one person cannot run the show. It means that as a researcher point of view or any R&D development, I think we need to. I think usual way is that I think one particular people will focus on the product, what they call mining, and some people are focusing on the battery fabrication, or sometimes a very high-fi, like like more way of how to standardize the things, and some people are developing in the electrolytes, or some people are developing only in cathodes, some people are developing on anodes. So as a researcher point of view, that suppose now present challenges as a academic research, what way we can do to look is that how to improve the energy density, or is there any way to reduce the cost? Only way is that either you can do in a small scale. Still, people, especially novel material processing, is very important. At least in terms of which materials are good, this way we can screen the thing. Once we are uh, fine with the small quantity, I think any again industry or any other X people, they can look into the formulas, or they can continue it in a large scale. Again, if you go to industry, so for example, here 5 grams of samples you can prepare. There nearly tons of the nearly or more like 1 ton, 2 ton quantity they have to prepare in a almost like nearly, for example, here people want to get to the graphite nearly around 4,500 tons per year. So that much of the big large scale production facilities are available in the industry. Now, what are the importance of energy storage? For example, you talk any batteries, I think all people are familiar about the, if you want to run with EV, or you would like to store the, for example, energy from solar or wind energy, or people are talking about the smart houses, or like smart residential or smart cities for that smart building for that case. So that the idea is that whatever the way you do, it should be less pollution. So that's why this is another again although it is a real cartoon, really I think cost consideration is also major things you have to take into consideration. So I think these are old data, still the prices keep on rising. So overall summary as a the main objective is that I think the CO2 means pollution is also going to reduce, is lesser, that is very important. So you can see if you talk about the, suppose if you need a smart grid or electric vehicles, you need almost like 100 kilowatt hours, and so for this case, I think we minimum, so we need, so for example, higher the things, we need more materials, and also again the cost is also take into consideration. For example, the portable applications or medical devices, I think for them it assumes the materials you need a small quantity, and also especially for the space. So for them is the cost is not the main criteria, especially for the all the applications where everybody wants to come and people want to buy the EV vehicles. I think they're going to consider about the cost. So that's why still, so there is extensive research is going on, especially in your industry, in terms of the material production, so that they can produce in the materials in low cost, so that we can reduce further. So there is a way it is going on. So again, I think this pollution, so not only in the throughout the world, I think irrespective, slightly the number maybe it varies. So that's why there is a way people want to replace. That's why there is huge interest in terms of the academic as well as the industry, and also in government. Also, there's giving a lot of rebates to promote this technology. So another important is especially EV. Sometimes people are talking about the solar energy. Suppose you like to store the solar energy, we need something like low cost, affordable battery pack. So that's why. So again, the importance of this battery pack or electrochemistry. So in this particular things. So again, I think some people are in the engineer. So sometimes people are working with autonomous electric vehicles. So it will use us what they call as artificial intelligence, LIDAR, and radar type of sensing technology. So major benefits, again, we can reduce the lowering of fuel consumptions, and also we can reduce the CO2 emissions, and also we can reduce the traffic consumption, etc. So at the end, so these are the revenues these are taken from the literature. And another important point of use of autonomous electrical driverless vehicles, we can reduce almost like 90% vehicular crashes. So in the typical autonomous vehicles, again, you can see that compared to we need a sensor, and then, for example, in a computer, example, we need something like, for example, backside they put it the battery pack or engine, etc. So again, it clearly shows that there are a lot of opportunities, like not a one-man show, so that we need the importance of the materials, mechanical, and also at the end we need electrical and computer engineers to talk together so that we have to make programming. At the end, we need a smart infrastructure, or for example, we need how to be good infrastructure to our roads. Again, you talk with the civil engineers, etc. So that's why it is like a multidisciplinary area of research. So what we learn from the, for example, this college or the technology, what you're learning, so later you're going to adapt in a future. So that's why it is like so these are the different type of companies are investing. I think all people are familiar about this particular example. Tesla already is in the market, and especially Toyota. These are the very extensive interest is going on, especially in terms of material development, the electrode and technology, etc. So now I'm going to little bit slowly so that how the real topic of the how the component. I think all people are using this type of mobile phones. You may see something like somewhere if you open that one, you may see this type of pose cell. So, for example, positive, negative. So, it is this terminology is common if you take any type of the cells or primary or secondary batteries. Exactly, you can see some positive, negative. Only the primary. I think all people are familiar about this electrochemical. So these batteries are the devices which convert electrical energy, what is chemical energy into electrical energy. We broadly classified into the primary and secondary batteries. Among them, lithium batteries are the rechargeable or secondary batteries. So now I'm going to introduce, for example, irrespective of the if your battery using your mobile phones or if you the same type of material they put it in the cylindrical cells, the laptop they can use, or so if you'd like to run with electric vehicles, they put it in the big type of modules. Means so many number of the 18650 cells put it in the this type of stack. So these are the big depending on the requirement they can do, and then they'll try to put it in this type of a big stack and in the for example in car. Again, it depends on the what they call a usage and the energy requirement. Different type of the things is available. So what I'm mentioning, the materials are same, either cathode, anode are same. Only thing we need a. So that's why. So although as a researcher point of view, we don't have any capabilities. Or for example, you want to fabricate big battery packs is difficult. The reason is that suppose you want to prepare nearly, for example, 1 kg of the compound or 1 2 kg they want to fabricate, or everything is automated. That's why we need the initial investment. That's why usual way the laboratory people can concentrate about this type of not only laboratory in any R&D, any industry. They first they'll do coin cell. Once they're happy, they can go for this particular pouch cell, etc. So that's why any research R&D or understanding the fundamentals, I think that is very important for the irrespective of the any materials from the starting stage to for real applications. So now I think people may ask you that, for example, your Tesla vehicles again, so it contains the battery weight is nearly 540 kilogram. So it uses nearly 7,100 number of cylindrical 18650 cell, and it uses something like NCA means nickel, cobalt, aluminum. I'm going to discuss about the like future what is chemistry of this particular compounds in a coming slide. So what I'm mentioning that suppose as a research point of view that so how to reduce the number of cells? For example, instead of 7,100, is there any possibility go to 3,500 or 600? So only way is to increase the energy density. So for example, for that case, always you to look for the higher voltage and higher capacity. So these are the little bit fundamentals. So that's very important. So and automatically once you reduce the weight and then cost, again cost will vary depending on the materials of the initial raw material. I'm going to discuss about the coming slides. So what are the important points you have to remember? Suppose, for example, you talk about electric vehicle on a smart grid. Always you have to look for high energy density and power density. This is very important point to remember. I'm going to explain how to calculate the energy density of the particular batteries. And again, it is very important any battery do fabricate it adapt to climate conditions. Since I mentioned that it contains some electrolyte, so If it is too low temperature, the electrolyte will freeze. Sometimes conductivity reduces. I think some people are doing with the physicist or any polymer chemist. If you do conductivity studies of the electrolyte, you know that automatically conductivity decreases with respect to temperature. And also time with the high temperature slightly reasonably good. Sometimes too high also. Sometimes because of flammabilities and sometimes safety issues and long term cycle life. It is very important. Sometimes once I purchase a battery pack or any car, so they will tell that 360 or 350 kilometer per hour, kilometer per charge or anything without any problem with respect to any road condition. It will work, then it's good. So that's why again it depends on how the driving conditions and traffic. So many factors are there. So I'm going to not much time to discuss two details and how the driving patterns or the road conditions going to vary. Although what are they mention that particular things, for example. And again, the high capacity, there is a way automatically once you go to this, these are interrelated. And Coulombic efficiency is very important in the sense that so always charge and discharge should be almost same, so that we have to get some 99%. Impedance is the one, so we have to look for the low resistance is very important, and fast charging. So I think the especially the resistance of the cell is nothing but usual way is that it will monitor the for example, in industry, what they do is that they will monitor the cell with respect to time and year and cycle number, etc. I think usual way is that if it's a good batteries, resistance it won't vary with respect to time. So if it's varying too much, too high, something is going to happen. Something is going to either your material degradation or problem with the electrolyte or some other current collector, etc. We can do. So in summary, it is very important. Other point is the fast charging. I think people, electrical engineers, I think we have capabilities to design very fast chargers. So now people may ask that shall we reduce to time with 5 to 10 minutes? Only way is increase the current. Yes, it is possible. The main issue is that these are solid state materials. There is a problem with the diffusion of lithium or any type of lithium or sodium or any type of ions as move. So automatically, so usual way is the industry in order to get a maximum capacity. So they have something at some limit and they don't go too high current and then too low also. So in between, so that's why these are all battery management or package it will do. So that's why the charges are going to built by electrical engineers. Afterwards, we have to look for more safety, low cost, and toxicity is very important. And at the end, always what are the research you do in either a battery or solar or anything, sustainability is very important. Recycling, that's why it is always people have to think about how to recycle the material in a proper way. I think this technology already known, only is a matter of cost and then how the things is going on. So that's why now, I think one quick slide I'm mentioning that it is applies to not only lithium, sodium, potassium. Exactly the same story is happening. Usual way is the mining and processing in the sense that if you want to work with any materials for lithium or sodium or any potassium battery, we need a respective mineral. For example, so if you want to lithium battery, we need a lithium containing salt, or if we need a lithium source, and also nickel, cobalt, manganese. So these are the very important source. For example, you want to talk about the cathode and iron, phosphorus. These are all important points. Especially for the anode production, we need a graphite. So, for example, if you use a sodium batteries, we need something like soft carbon. Again, that one we use only with artificially people can with the petroleum coke they can do. So this graphite usually either you can get natural graphite and another way is artificial with the petroleum pitch. They can heat the sample with high temperature, nearly around 2500 degrees. So then they can get a graphitic form of the graphite. So each technology, because in terms of cost wise, I think always people prefer to the natural because cost will be lower. And copper, aluminum, steel for cell manufacturing, especially for the battery pack. And we need something rare earth like neodymium and dysprosium, so permanent magnet for this. So that's why, especially the mining, especially we need this part, we need a proper mineral. For example, I'm mentioning that although it's very simple, so if you talk about this another extreme part of mining, you can see that something like minerals. Nearly 30 tons of the mineral gives a 30 kg of cobalt. See, that's why how much things is going. That's why cost is automatically cobalt is a bit higher. nearly 5 tons of the mineral will give 60 kg of nickel. 6 tons of mineral gives copper. So especially 1 ton of the mineral gives nearly 90 kgs of the graphite. So that's why, so the cost will vary depending on how the what they call a scarcity. The same thing applies to our gold. That's why nearly ppm level we can get. That's why the cost of gold is or platinum is expensive. So afterwards, when characterization, manufacturing, and end use, either you want to be EVs or smart grid, or anyway, when the material is ready, only we need a matter of how the packaging technology, everything is automated and they can do. And at the end, people have to do recycling. These are typical some of the old data, how the cost vary depending on your cathode, anode, separator, uh, foil, etc. That's the typical some of the old example. So anyway, in summary, so always you to remember if you talk about the sodium, anyway, we need a respective uh, what they call a mineral. So people may ask you that in terms of the availability, so sodium is slightly higher, more abundant. Again, we have some other problems also there, although it is not so very simple because I'm going to talk about in terms of electrochemical potentials and stability. So handling the sodium or potassium compounds are not so easy. That's why so still maybe another 5 to 10 years still lithium may be promising once the technology been matured and then if people are not able to look for any alternative sources then still sodium I think they will concentrate on that on how to stabilize this type of materials. So now I think I would like to mention that sodium batteries is not a really new one. So you can see that before lithium batteries originated with all the research has started from sodium chemistry. It's called sodium cobalt oxide is a very well known layer type compounds. I think this one worked with my previous laboratory long back in France, like 1973 is almost like when I born at the time. Always at the time, people again the new discovery at the time, people always solid state chemist try to understand how the intercalations and then understand the physical properties, electrical, etc. So finally, I think a nice idea with Professor John Goodenough visited their laboratory and finally he replaced the sodium by lithium. So we know that lithium compounds are easier to prepare and easier to have, stay more stable. And once already it's demonstrated with a simple the virtual paper, then followed by Sony, we got the nice idea, and then this type of particular batteries have been commercialized. Uh, Again, now it is more popular, especially this batteries. So now, still, I think still there is a lot of interest how to reduce the cost, especially in terms of EV, grid, and other type of the applications. Now, I think it is very important always you to remember the cathode. I already discussed about this particular things. Suppose cathode means, for example, if you're talking about lithium batteries, we need a lithium containing uh, material, for example, lithium cobalt oxide, you can see. And if you talk about lithium iron phosphate, so anything, if you talk about lithium, respective inorganic oxides or phosphates are needed. The reason is that we have some examples in terms of organic cathodes also there. The problem is the voltage is slightly lower. That's why most popular is the inorganic oxide. Suppose same story, if you talk about the positive electrodes, lithium is replaced by, for example, sodium cobalt oxide. Exactly, they call as sodium batteries. Or if you replace potassium, you need a respective potassium containing inorganic oxide. So always remember, so this is one side. Another side is usually most commonly, suppose in the laboratories, people want to do either by lithium metal, you can do again the cost wise is slight. So, or some most commonly for the industry, suppose you want to use something like graphite. These are like almost both are layer type structures. So this for the graphite used for the lithium batteries. For example, you want to be used for the sodium battery, we need a soft carbon. So that's why again, as we know that in the simple electrochemistry or what is the ionic radius consideration. So the lithium has a smaller ionic radius when compared to this sodium, potassium. So automatically we know that higher the smaller the ion, more mobility. So that's why sometimes in terms of mobility issues, lithium will be really good when compared to the so potassium or sodium or potassium. So sometimes people want to get more capacity. The graphite mix is a silicon. The reason is that voltage potential is matching. That's why, and some metal oxides. And the story is same again. People want to talk about the calcium. They can try to replace with calcium, sodium, zinc, magnesium, etc., etc. I can do, or if you do aluminum, that's why we call aluminum batteries, etc. Overall summary is that since if you the same electrochemistry with the same knowledge of oxidation reduction, or the same knowledge, we can develop any type of the metal ion batteries, either lithium, sodium, potassium, etc. Again, although mechanism may be same, again the main issue is that how the capacity or mobility, how the some materials are really good in terms of the voltage. So that's why as an industry they are looking for the what they call as higher voltage, somewhere there is reasonably flat potential for the practical applications. I think the word we are going to use something like oxidation, analytic scan, positive current. State of charge is nothing but what they call as the charge. DOC means the state of discharge. I think these are the word people use. For example, electrical engineers, once you purchase the pack, they'll tell SO, how much SOC. So these are the words you have to remember. And also electrolyte is the one. So usually we use something like 1 molar LiPFC, CTMCs, ionic liquid, polymer electrolyte, and solid electrolyte. So these are a very important point you have to take into consideration. Current collectors, we use something like copper foil and aluminum foil for especially for this one. The reason is that copper may not, we know that copper metal is very difficult to reduce for lower. If we use aluminum to here, in addition to reduction, it form alloy with the lithium. That's why. So we need something, especially for here, cathode side. Uh, Copper will oxidize above 3.5 volts. Aluminum is a little more stable up to 5 volts. That's why we can use this aluminum as a current collector. We use a binder, for example, PVDF. See, like these are it is idea of binder is just stick the sample on the particular current collector, and we use something like water-based binder, especially you want to graphite, SPR. These are the things people are going to. Or sometimes we want to improve the conductivity. We can use something like conducting carbon, etc. Anyway, people are interested. People if want to see the early history or want to be more details, then we can look into this particular paper. I think these are the word people sometimes if you are any mechanical engineer, usually we call as composite materials, usually the electrodes. It looks like, for example, any metal oxides, carbon binder all together. It looks like this way. This is going to stick on the current collector. Usually this is called as a what they call electrodes, and these electrodes we can do a lot of electrochemical testing. I think 2019, all people are familiar about 2019 Nobel Prize is given with the well-known chemist from solid state Professor John Goodenough. The one of the oldest Nobel laureate won the Nobel Prize. So in chemistry. So in addition to all three persons, I think Michel Armand also play an important role in the early development of polymer light and then intercalation concept. Again, remember, although so all the original ideas coming from the original paper, for example, this sodium battery. So that's why sometimes, so that's why, so all the ideas, not all people cannot get the prize. So that's why sometimes, so new ideas always. That's why as academic researchers, this we report what are the results you have. So now I'm going to introduce the principle of the lithium-ion batteries. I think all people are familiar about the batteries. So it is nothing but shuttling of the lithium between the cathode. During charge, lithium move from the cathode to anode, where the electron will pass to the external circuit. During discharge, again, lithium will go back to the original state. That's why we call it the rechargeable. So always you remember here cobalt 3 plus is there, something like a metal oxide. So once you remove the lithium charges to balance, so here that's why we call it the oxidation, means 3 plus to 4 plus. That's why we call it the this called oxidation. So so again go back to the original state is a discharge, means cobalt again go back to the 3 plus to 4 plus. So it is typical the same thing I'm representing the current versus potential plots. When you remove the lithium from the structure, means cobalt 3 plus to 4 plus means oxidation. Again, oxidation, reduction. So usual way is that this way we call as a rechargeable batteries. As a layman, so always you do any research, you have to get a positive current and negative current to indicate that okay, your material is reversible and then it is good for the batteries. Always good point is that if it is a good cathode, so always you have to look for the flat potential. For example, here lithium iron phosphate is 3.5. For example, cathode aluminum lithium cobalt is nearly 3.9 or some depending on the chemistry of this one we can get the voltage and so usually the what they call as the cell voltage nothing but difference between the cathode minus anode. For example, top means 4 volts minus 0.25. So good way is that if you want to get high energy density, so what is the best way is that we need a higher difference between charge and the discharge potentials, followed by the capacity should be in the, for example, so this voltage x-axis should be higher is good. So now I think again, so now that is simple word is, for example, if you, since a layman, oxidation reduction or intercalation there is enough. Suppose if you want to write a papers in a specialized journal, I think we need something like, for example, so electrochemical mechanisms. So usually, most commonly, what people will use is the intercalation, deintercalation mechanism. So in the sense that here, when topotactic reaction occurs, we play with 1 or 2 lithium. The advantage of this particular thing is that we don't see any volume variation, etc. And then, so this including a commercial graphite or cathodes undergo this type of mechanism. So for example, we talk about the tin silicon, it undergoes alloy forming elements. So that's why we can see once it is forming the huge volume expansion occurs. So idea is that in order to reduce this expansion, so what people do is either material should prepare in the nanoscale, disperse in the carbon matrix so that we can reduce the buffer the volume variation. And again, we can use something like lot of metal oxides, inorganic. There is a lot of bunch of materials are there again. So there is a limitation in terms of applications. So the reason is that although we get higher potential, higher capacity, the practically these materials may not be useful because of we don't have any proper catching, proper matching, what they call as cathode materials. So similarly, so depending on the voltage, we can call as the alloying and conversion. So I'm telling this as a electrochemist. I think once you write a mechanism, so you have to write a proper mechanism appropriately accordingly. That will be good. So now, in summary, what I'll suppose if any researcher want, any chemist want to do any new ideal cathode and anode materials, what are the important points to remember? Either your sodium batteries or potassium, always you have to look for a material should be low atomic weight. So theoretical capacity can calculate by this one well-known Faraday's equation, the number of lithium into that total weight divided by molecular weight of the material. So automatically lower molecular weight is good for the in order to get higher theoretical capacity. For example, you can do lithium cobalt oxide, you can try to put one lithium here or 0.5 lithium, usually 0.5 lithium divided by molecular weight is around 97, then theoretically you can calculate that, for example, 270 or so depending on that one we can calculate. For example, lithium iron phosphate, exactly the same thing, one lithium, and then you can put the molecular weight of any material, we can get a theoretical capacity. The same thing applies to any type of the oxide, for example, nickel oxide. Any oxide you can put accordingly how much lithium can be reducing, accordingly you can back calculate and you can get a theoretical capacity. So another important point we already discussed about the anodes, you have to get a lower discharge potentials. So graphite is more popular because of the, you see that we can get nearly lower discharge potentials. As a consequence, we can get a reasonably good voltage in the sense that the difference between charge minus discharge should be higher. What they call as the voltage cell is nothing but average potential cathode minus anode. I think these are all things we learn about the what we learned from the electrochemistry. That's why some, for example, nonist equation or free energy. So these are all the, or sometimes in electrochemistry we are learning about the Butler-Volmer equations or some, a lot of these equations are really useful to understand. Although it's very simple in reality, if you go more depth, I think what we learned from the electrochemistry, so you're going to use it for the real applications. So it is very important. So the voltage of cell is energy density is nothing but voltage of the cell multiplied by capacity. So good way is that higher capacity also needed and higher voltage. So these are the important point you have to take into consideration if you want to design a new material. And also another important point to remember is that cathode and anode material must not be soluble with a solvent, in the sense that always this is very important point. Sometimes people design a new materials, sometimes your materials reacting with the electrolyte, so that may not be really good. It's a good sign. So at least you have to look into these are also an important point. And at the end, we need a materials to be mixed ion conductor, in the sense that people want to be fast charging. For that case, if it's insulator material, they may not be really good. So that's why, and still people can do further improve some coatings also they can do, take into consideration. In summary, why lithium batteries are because of lightweight, high energy density and gravimetric energy density, and that one we can use it for a lot of applications, especially voltage wise, it's good, and especially the space and other type of the applications people can use. So quickly I'll go through the electrolyte again. The another part is the electrolyte itself. It is another 1 hour talk I can also give. So due to time limitations, I'm going to skip. So as a layman, just always remember if it's a lithium battery, we need a lithium containing salt or sodium, etc. Accordingly, we need a respective salt. So that's why we need something like organic solvents. So advantage of this particular liquid electrolyte is reasonably good conductivity, and we have something like leakage problems and flammability issues, and that's why people have used something like lithium polymer electrolyte again. Polymer again, you take into lithium polyethylene oxide, or sometimes they mix some ionic liquid, etc. So again, also sometimes polymer electrolyte is in order to make a reasonably good conductivity, we need to materials have to slightly heat temperature, maybe 40 to 50 degree, depending on the uh, like polymer and salt combinations. So separator is also very important. The purpose of separator to avoid short circuit. Again, it is also another area. The cell guard is the one. So the polymer separator, porous polymer membrane. Again, these are very important point. Thickness is 25 micrometer. Porosity is 40%. Permeability is etc. So this point you have to take into consideration. So recently, due to flammability issues, I think people have used something like a solid electrolyte again. So the issue is that how to make a good contact is also a big issue, especially for this solid state electrolyte. Again, we need something like high ionic conductivity and low electronic conductivity, and then these are very important point you have to take into consideration. So although it is very simple in practically, if you sinter the sample with high temperature, sometimes it may react with your electrolyte and the cathodes interface problems. Sometimes you may get some conductivity reduction. Also, so these are very important, means good chemical stability and no crystal structure or variation, etc. I can take into consideration. So, so anyway, there is a lot of bunch of materials. I don't have time to discuss since either sulfide seems to be good because of easier to fabricate. Again, another issue is the sulfides are not stable. They're all the another little bit drawback. And oxides also seems to be good. Again, we need to process this material. We need high temperature, so there's a little bit drawback. Again, sometimes it is not so easy once you may press the two electrodes or electrolyte, and we need a proper contact, especially fabrication. It's a little bit complicated. So now the material processing and characterization techniques. So whatever the research we do, so it's very important always you to depending on the available facilities, and then what they call as depending on the which type of oxides, which cathode, either cathode or anode, whatever the electrolyte, we need appropriate material processing, and then so it's very important. Again, the materials in summary, there is a lot of all those same materials we can different type of applications also we can do. Sometimes people can focus in particular areas, or we have some collaboration you can do within the department. Some people are expert in the different areas, or same materials people are interested. They can focus some other, for example, titanium dioxide. People can use energy storage, or sometimes people want to do with solar cells. Some people have expertise. They can do accordingly, or photocatalysis, etc. I can do. So now I think usual way is that now we have capabilities in laboratory with we can prepare the either different type of shapes or whatever either nano submicron size materials we can do with these capabilities we have now. The industry, I think they're able to fabricate the materials either depending on the precise shapes, nearly tons of the quantity they're able to. So again, the thanks to chemical engineers, so they have been developed the big reactors, how to not to make a uniform size materials, etc. So now regarding material synthesis and characterization, again, chemical methods are really good. Advantage is that easier to fabricate, and you need a simple beaker, and then with our aluminum crucible is needed. Advantage is that we can prepare in large scale. So again, I think, for example, 2 to 3 elements are there. I think chemical methods are good because the oxidation state, ionic ready, everything you can match accordingly, we can prepare. So again, other physical methods, sometimes you want to thin films or all solid, sometimes all solid state microbatteries you can prepare by using this sputtering technique, and atomic layer deposit not to make coating, etc. I can do. So again, so this is in summary, so that always is very important. We need appropriate technique. So sometimes you want to be some coating, so you need R, sometimes some nano size coating R. So for example, in silicon wafers, we want to develop something like some nano size coating also you can do by using something like atomic layer deposition, etc. So again, if you're a metallurgist or mechanical engineers, people, irrespective of nano size, they need some composites, so good mechanical properties. For that case, we have to press the material by either hard pressing or spark plasma sintering or what they call the additive manufacturing, 3D printing techniques people can do again. So again, this type of some common applications we have to look into this. For example, all solid state batteries or solid oxide fuel cells and composite, etc. We can do. So now it's very important, although it is not my so due to time limitations. Quickly, I'll go through X-ray is a very useful tool since you are preparing any oxides type of material or oxides or any type of the ceramic material. I think X-ray will be useful to understand the how the phases, etc. And sometimes you can do some fancy technique, neutron, X-ray absorption. There are all things only you can do if you have facilities and thin films like RBS and nuclear reactions and OGR electron spectroscopy, etc. Always remember, so XPS, so sometimes although there is a limitation of the depth, still these techniques people want to be oxidation state, etc. I can do. Or for example, BET, Raman, etc. I can do to understand thing density. And for example, another important point to remember is the galvanostatic charge discharge cycling. And the impedance analysis also is very important to understand the, for example, so this technique is very useful to understand the how the charge is charged. For example, understand the reaction mechanism, electrode kinetics, etc. I think all people are familiar about the galvanostatic potential. This technique is almost common for any type of any electroanalytical techniques, etc. Again, the morphology, etc. I can do. So these are the sometimes you can do some fancy technique, for example, NMR or some in situ technique just to monitor the things, what is going to happen with respect to real time battery, etc. I can do. So these are all the setup is also available. So these are the battery tester. It's nothing but it will monitor the voltage as a function of time, and then impedance analyzer just to see the resistance or conductivity or cyclic voltammetry, and then it is a different way of various analytical techniques are possible. So these are the battery test called a fast charger. So for example, if you're talking about the electrical engineers, your capabilities, you can tell that okay, I need this particular current to apply and this particular voltage. Everything you can design the depending on requirement. So that's why, although it's very simple in really research, they can do depending on the current requirement. Accordingly, they can do. Advantage of this laboratory fast charger is you can monitor, you can see real time how it is going to happening. In practically your commercial, your EV charger, anything, just only you hook this particular things and particular thing only. You don't worry about what is going to happening. All BMS software has been installed, everything. So depending on chemistry of particular pack, and then they can everything is monitored, so you don't need to worry about this one. So how to calculate capacity is nothing but step time into current or weight of the material. That way we can calculate the things. And then so in summary, always you to look for the higher charge discharge potential. This point you have to take into consideration. So in order to get the high energy density is nothing but already I discussed about the voltage. For example, 18650 voltage into battery rating divided by battery weight, we can calculate. Or sometimes people call it the energy density or specific energy density. The word are all, like terminology is almost same. So that's why, and power density, same thing. Energy density, power density is meant voltage into current. That's the way we can apply. And then these are the formulas already discussed about how to calculate the theoretical capacity of materials. And then so irreversible capacity is nothing but difference in the discharge minus charge. So these are the very important point to remember. Lower is good. So for example, graphite. So it is see this is lower discharge capacity when compared to your other form. For example, you can see here this is like fuel air graphene. Although we get some high capacity, practically this capacity may not be really useful. So in summary, capacity fading, how we can do, for example, second cycle and n cycle. So we can see how much capacity fading. Coulombic efficiency is nothing but difference between discharge minus charge capacity. So that way we can usually 99% is good mostly. So that's why the problem is how to improve the Coulombic efficiency in the first cycle is a little bit challenge now, irrespective of any battery technology. So I think people may ask you why the fast charging will not work. You can see, for example, 1C means like nearly 1 hour, 5C means almost like 12 minutes. So okay. So remember always the reason here is that sometimes we do fast charging. So for example, almost same bigger particle, the all material if you do with higher current rate, all material may not be participating. So the main reason is that due to the mass transport, like a diffusion mass transport limitations. So that's why in practically, I think if you have something like smaller, what they call as nano size materials or optimum particles are really good. So usually, I think as the industry, they will tell the somewhere so that to balance the capacity, and that's why they can do what they call as doing BMS management. They fix the current. That's why sometimes you would wait for example, some battery packs you would wait for overnight or 6 to 7 hours depending on the different type. Again, there is a lot of interesting things happening in terms of the technology, how they can do either by electrode design, improvement in the electronic conductivity of the electrode, electrolyte, cathode and anode, etc. Electrode design. So these are the different way and appropriate electrode thinking. There is also a lot of interesting things that's going on. This, especially this making the electrode. This one itself is a big one particular area of people are focusing. And that's why we need a lot of effort and then time to optimization. So I think all people are familiar about this CB. I don't have time. This quickly I'll go through. So good thing is that color the same thing like oxidation, reduction, and sometimes you may get some supercapacitor. You may get something depending on carbon or metal oxide. You may get some different type of shapes, etc. So usually my suggestion is that if it is solid state materials, always do with a slow scan. Don't do with fast scan because sometimes you may not get any signal. So as a layman, we get oxidation reduction potential, reversibility, and then we can see depending on the materials, automatically we can get a respective redox potentials. That way we can get the information, etc. So in summary, what are the things we can get on CV? So almost I finished 50 minutes. Okay. So this similarly we can get a supercapacitor depending on the oxides, etc. So another important point you have to remember, cyclic voltammetry. This is very useful tool just to understand the redox potential, oxidation reduction. So what we learned from the Randall's equation from the practically this the same thing you are going to adopt with respect to scan rate, thickness, etc. So impedance spectroscopy is also very useful tool. So since I don't have much time, quickly I'll go through. So if anybody is interested, I can spend EAS itself is a 1 hour 2 hours talk. So advantage of this one is that just needs the conductivity and respect to any type of the areas, for example, fuel cells, supercapacitor, or photoelectrochemical cells. Try to understand the electrode electrolyte interfaces. Either sometimes depending on the electrodes, with the thickness, you can calculate the conductivity, or you can do 2 electrodes or 3 electrodes. You can do impedance response, or sometimes very complex like 3 electrode systems. Also, you can design for the special setup. So if it is solids, you can make a grind boundary resistance, and we can see the different type of conductivity variation, etc. I can do. If it is a lithium ion cell, we can see depending on the voltage, either by surface film resistance or charge transfer bulk, etc. I can do. So always remember, once you do, that's why we need something like understanding the impedance, for example, resistance, capacitor, some knowledge is needed. That's why idea is that once you set up, once you do simple like electrochem impedance spectra, once you get some literature based on that, then please read the literature. Accordingly, you can do appropriate equivalent electrical circuit model, and then they can do. You can fit the model, etc. I can do. In summary, although chemistry we can do, so if you want to make a big vehicles, again is the importance of we need the power electronics, electric machines, energy management. Although with chemistry is sometimes small part, in reality you want to design all the engineering, everything, both mechanical, automobile, and electrical, and sometimes computer engineers, and then that's why it is a multidisciplinary area of research. So quickly I go through, since my time is, although so again quickly I'll go through the important one, an example with the cathodes. So the main issue is presently we have the capacities limitation. That's why now maximum we can go I think around 240 or 200 milliamp per gram. That's why, so there is a lot of scope. If anybody new materials, we can extend this particular cathode area, especially for anode. There is a bunch of material. Again, there's some limitation, some problem is there. So So usually most commonly the graphite because of the lower discharge potentials, and then we can get reasonably good energy density. So these are the promising, for example, nickel, lithium, nickel, manganese, different type of 80%. And so if you do higher nickel, automatically more capacity. So sometimes depending on the compositions they can do, or sometimes they may use like lithium, nickel, aluminum, small doped aluminum also they can do. So this is the way we can, and iron phosphate, etc. So due to time limitations, I'm going to explain one particular example. So how to prepare with a simple tube furnace, something like lithium, vanadium, fluorophosphate, iron phosphate, etc. I can do. So with the carbon, we can reduce the materials from higher oxidation to lower oxidation state. We need appropriate carbon, and then with the appropriate temperature, put it in an argon furnace. We can get respective oxides, or we want to purge with ammonia gas. We can get some nitrates, etc., etc. Can do. So there is I think since the facilities are there, you can do anything, whatever the way, depending on applications, you can concentrate. So as a electrochemistry point of view, it's always you go to 3 plus to 4 plus is very important. Like here is a, so again, we have to characterize them with a simple XRD, see the what type of phases are good. And once you're done, then we have to make a slurry. So active material binder and carbon mixed together, finally coat the sample. And once twin roller and pouch is, like for example, punch, etc. I can do finally once cell is ready, finally for example, this type of the 1860 16 diameter, I can do punch the things and then dry the things. You do it in a glove box and cell is ready. Usual way is that this way the laboratory scale or any R&D or industry they do. Once they're happy, they can go for this large scale production. These are all the things nearly kilograms. The quantities are needed, so that's why we need. That's why most of the students are not interested to prepare the kilograms. So mostly they go for the small cell once they're happy. Or so usual way is that sometimes if you want to be electrical or mechanical engineer, you may buy the battery pack from the supplier, and then at least idea is that I want you to know what type of the safety limit is very important. Don't exceed the limit. What are the things assessed? So this typically, for example, bottom cap all together, and finally this the cathode, separator, and electrolyte, and then finally lithium metal or graphite. Finally put that one. Finally cell is ready. Once so usually we need something like a capacitive or cycle number, and we can see what type of profile. As a depending on 3 cathodes, you can see 1, 2, 3. So always good cathodes would look for higher charge potentials. So automatically we can get high energy densities. So anyway, we can do the various XRD and impedance. They try to understand what is going to happen with respect to cycle number, etc. So in summary, so anyway, these are the as a layman, so very always look for the higher charge potentials, etc. I can do, and then so anyway, so similarly we can do some new materials. Since that my time is going up, so I don't have time to discuss too details. And this again is very important. Some new example is 4 volts materials have been developed. And then so regarding the potassium ion battery, we tried sodium also. Sodium, so lithium seems to be good, followed by sodium. And potassium, you see, sometimes we may get capacity is a little bit lower. The main issue, the mobility issue, and there is a lot of development in the electrolyte, etc. That's why later our first report they've been extended by some Japanese group, and there have been small improvement have been further noticed, especially this type of the potassium containing oxide. So quickly I'll go through what I'm telling, that we early report followed by including novel already they've been extended. I think these compounds have been more popular. Quickly I'll go through the stop this this particular synthesis. Now I think again quickly what is the some people may ask you the sodium. Yes, cost wise sodium batteries, sodium ions will be lower when compared to lithium. Again, some other limitation is the what I told you, the mobility issues, and then due to ionic difference ionic radius, and they're not so stable when compared to your lithium. So for example, prepare sample, a little bit hygroscopic and handling of the materials. Yeah, these are a lot of bunch of materials also there. So what I'm telling, one example is the lithium versus means 4.2 volts and 3.5. It means that energy density with lithium will be higher when compared to sodium. Still, if you want to be stationary applications, sodium seems to be okay, promising. I think we get 20% of the reduction of the cost we can reduce further. So anyway, I think some organic cathodes also. One quick word I'm telling, that always we have to get some voltage difference in the charge discharge potential, not too high. So more popular is what inorganic oxides are a little bit better than good than the organic compound because of the we don't get any expected voltage in the energy density in terms of applications. Okay, I'll go through quickly since my time is up. Again, I discussed about the graphite. There is a lot of interesting things is that we have to look for the lower discharge potentials, and then these are the different type of strategies people have been done. So again, we can do a lot of mechanisms. So due to time limitations, I'll go through alloy tin and silicon seems to be good for alloy gas forming elements. Either you can do a lot of interesting oxides. You can do it again. The story is that we need appropriate. Interesting thing is that how to reduce the voltage is are, for example, irreversible capacitance first cycle is very important. So there's a lot of bunch of material. Again, the main challenge here is that how to reduce the voltage hysteresis on the lower. That's why electrochemistry will play an important role. That's why always is a good idea that how to have tricks to reduce the charge discharge potential to the lower limit is really good for the application. Again, you can do either by nitrides, etc. I can do. Similarly, either you can do discharge potentials to the 1.5. Also, you can do LTO, etc. So either you can do full cells since my time is up, and again quickly I'll go through. Sometimes you same TiO2. Either you can do simple approaches people can do with the molten salt approach. We can prepare sample. This is a way we can universal. We've been look into a lot of oxides. Quickly I'll go through. So what I'm one word I'm mentioning that nano seems to be nano to micron size. That's why we can see the difference in the performance. So overall summary is that some materials, I think one last word I'm telling that for thermal stability is very important. Sometimes battery may catch fire. That may be due to the lot of problems either by cathode failure, anode failure, and separator and etc. Take into consideration. So again, in terms of anodes, we have to be due to solid electrolyte formation, decomposition, and then sometimes we may due to thermal runways, and sometimes rapid charging also not good. That's why it may due to the dendrite formation that the consequence short circuit. So these are all that's why sometimes people they use it depending on the which type of anodes. Accordingly, we need a appropriate current density. That's why they will not do. And overcharging for the cathode also same thing. So higher limit is not really good. And sometimes it may release oxygen from the electrolyte, which may lead to the combustion and electrolyte and separator failure. And sometimes in not suppress this one, we can use something fire rate or suppressions. And similarly, correct collector things. And these are the different ways we will do. Since I don't have time to discuss two details, okay. So again, we need a thermal management, safety device. These are all things. If you talk about the, for example, mechanical engineers, sometimes people may focus on particular area. Sometimes safety devices, for example, electrical engineers, they are looking to the how to do the sensing that inside the battery pack, etc. Can do. That's why it is like all the people have to work together to the. I think quickly I'll go through institute one word I'm telling them what are the safety limit they suggested. Try to restrict the voltage. What are the limit they mention according to the restrict. So it is very important. So reason is that sometimes to remove too much lithium, there may be due to oxygen release, or sometimes may slowly you may see the bulging of the batteries. Sometimes that's why there is safety limit to according to restrict, or so it may lead some flammability issues, or sometimes make a failure of the battery. So anyway, we can do some other fancy techniques. I don't have much time to discuss about all details. I think one last word I promise them, sustainability is also very important. Whatever the research you do, you have to make sure that recycle them in a properly. I think again remember nearly 11 million metric tons of battery discarded by 2030. Nearly so that's why it is our responsibility. We cannot throw these batteries, so to make a proper education. So we have to dispose in a proper way. So that the reason is that if you as a chemical waste again if you do dispose in a, for example in a soil or water, again we are going to contaminate the water. That's why we have to properly dispose. So either by direct recycling, people can do direct hydro and pyrometallurgy approaches. Among them, each technology, the usual way they will do in practically go for industry. They have a different way of segregating, and also they can dismantling the things they can do. Again, I think since my time is up, so usually with hydro means water based, sometimes we do acid leaching. Those are all things you can do, recover the materials. Again, each technology, again, we need something like some people will tell that acidic water, again, we have to neutralize them, we need some additional cost, and leaching it will take more time, etc. So pyrometallurgy approach, sometimes depending on some companies have been already demonstrated how to recover the materials. It is simple with heating the sample. For example, this one particular pyrometallurgy approach, for example, lithium cobalt oxide react with carbon, we can get lithium carbonate. It's not like we cannot get exactly lithium carbonate, LiCO2 we cannot get to the end. So always in terms of other lithium carbonate. That's why we need some different materials. For example, you see the NMC, we need lithium carbonate, nickel, all the 3-4 elements are doing proper. That's why the cost of the recycling, that's why it is going to vary. That's why sometimes as a cost included during the manufacturing process or some government initiatives and etc. that to take into consideration. Okay, similarly, different approaches also there. So either with sulfates, there are other chemistry we can do. So since I don't have time, again do a smelting approach also you can do. So this way we can get the recover the material. I think it's already exceeded the limit, almost like 1 hour, 5 minutes. So I think so my time is already. So these are the small conclusions. So what are the research? Although we claim so many materials, among them promising materials for using for your EV. So still there is a lot of scope to look for some high voltage or high energy density materials. And again, as an engineering point of chemical engineers always look for green synthesis, etc. in terms of the electrode electrolyte development. Overall summary, there is a lot of scope for new materials again. Also there is a lot of scope for the good high conductivity ionic polymer. Some people are working polymer chemistry. There is a lot of scope. Again, we need the cooperation between the scientists and engineers, for especially for the large scale application. And thank you very much. So I'm going to stop my presentation. So thank you very much. Okay. So now I think maybe we may have some.
Sir?
Yeah.
ಇಲ್ಲ, ಅವ್ರನ್ನ Sir, talk was really informative, sir. Sir, kindly accept our appreciation certificate, sir. Sir, on behalf of Don Bosco Institute of Technology, Principal Sir, and Department of Chemistry, I thank Dr. M.V. Reddy Sir for his informative talk. Thank you, sir. Feedback link is posted in the chat box. Kindly fill the feedback to get e-certificate. Sir?
Again, it is okay. Now it's okay.
Sir, thank you, sir.
Okay, then thank you very much, madam. We'll keep in touch. No problem. Thank you. Thank you. Okay?
Thank you, sir. Thank you.
Okay.
Thank you very much, sir,
Okay, then thank you very much, Manjuna. Thank you.
for your
Thank you. We'll keep
valuable
in
talk
touch.
on lithium-ion batteries.
Okay.
I thank all the participants. With this, I am going to end the meeting now. Thank you all. Stop recording.